Greetings, friends. Welcome to week 2 of the review for the final for Physics 4C. Because everything we do will show up on the final. So I figured I'd do you a favor and start reviewing so early. We got a PLC this week on refraction, and it's going to be the same style as last one, so that's going to be due Friday midnight meaning 11:59. So same quiz format. Let's see, anything else on that one? I don't think so. Just make sure you get that started and finished, and then homework 1 is going to be due this time next week. This is next Tuesday. Okay, we'll have plus quiz on that day, so that will be there. And that's a standard thing, so please be ready to expect that every time a homework set is due. Let's see. Regarding PLC 1, actually, I don't remember if I finished grading your section or not, but I'm mostly done with it, or I am done with it. I can't remember. I was a little interested to read some responses that all seemed pretty similar and pretty similar to an AI response. So just another friendly, casual, hey, please, maybe you didn't use, maybe you did, maybe you didn't, whatever, I don't know. But please refrain from doing that, okay? So in case you did do it, please don't have AI write your responses for questions, especially I'm thinking the last one in the last PLC. Speaking of which, I think that, and I don't quite remember exactly, but I think that nobody, or maybe perhaps one person, more than one person, I can think of maybe two or three people for that last PLC question on the mirrors, did not, or 2 or 3 people did draw a ray diagram to justify their answer. And that was fantastic. I love that. Most of you just tried to give a word argument. I would recommend, whenever possible, draw a diagram, because that's a major piece of learning in this class, okay? So think about when you are trying to justify an answer, and if you read carefully, it does say rank the mirrors by the amount of body the person can see, and explain your answer. So an explanation would be a drawing rather than trying to explain in words, hey, it's going to be this way. Well, a drawing will readily convey that information with no hesitation. So I would highly recommend incorporating drawings into your conceptual answers. So we've got that. Speaking of conceptual, I think tomorrow we will have a quiz, which will be a conceptual quiz on reflection. So we'll have a Wednesday quiz on reflection. Let's see, quiz. All right, so please be on the lookout for that, and let me know if there's any issues, but it will be same type of deal, available on Canvas. Question?
Do we include a screenshot from the simulator that you showed us instead of a hand-drawn, or would you prefer it to be a hand-drawn to explain on the PLCs?
If you use the simulator, that's fine. Hand-drawn is probably it's more tuned to the practice that you might need to have, right? So okay. In other words, right, like for this quiz, if you're gonna go knock out a quick drawing because you gotta get stuff done, you may not have time to use a simulator.
Okay, so you're not looking for like the precision, but just note or seeing that we understand the concept.
Yeah, and I don't expect a high level of precision from drawings like this. They're meant to be qualitative and convey the ideas that you're trying to argue.
Okay, and would you prefer us to use grid paper or is lined paper okay?
I have no preference on that. Totally up to you.
Okay, thank you very much.
Sure, no problem. Good question. All right, so we have finished reflection, at least the mirror part of it. We are going to come back to reflection a little bit, probably end of this week, just to have a slightly different viewpoint on how to think about it. But for today, what we're going to do is start talking about refraction. And refraction is basically another way that light rays can change their direction. So with a reflection, certainly hitting a surface and bouncing off is something that happens to light whenever it undergoes a change of medium. So whenever there's a difference in material that the light is propagating in, you'll likely see a reflection at the boundary between those two materials. And if you consider the two materials to be transparent, which in this case we're going to consider light as propagating from one material and into another material, so it's not opaque. We're thinking transparent. So for example, light in air going into glass, or perhaps water or something like that. We're going to find that it changes direction. So this is basically the change of direction of a light ray. And it's due to a change in medium. Now, when the medium changes, what we'll find is the speed. The light speed also changes. All right, so a change in the medium means that light was traveling at some speed, for example, here in air, and then it went into a block of glass, or here I have a block of plastic, okay? So it goes into a block of plastic like this, and as it comes in here, it's going at whatever speed light goes in air, which is pretty fast. It goes into here, it's going to slow down a little bit. So as it propagates through here, it's going to slow down. As it reemerges, it's going to go back to being normal light speed in air, okay? So that change of speed means that the rays actually also have the ability to change direction. And I want to kind of show you what I mean by that by using a drawing. So imagine that we have a boundary between two surfaces, and I'm going to roll a set of wheels connected by an axle on the surfaces. I'm going to go from the upper surface. Let's suppose this is a surface in which the wheels can roll quickly, and the lower surface down here is going to be a material in which the wheels roll slightly slower. Maybe it's like pavement onto grass or something like that, okay? So when it's pavement, it's quicker, or it's slightly faster wheel speed, and here on the grass, it's going to be slower. So I'm going to roll these wheels in. Here's one of the wheels connected by an axle. It's a little too big, the wheel over there. I'm going to thin that out. There we go. Okay, so here's my set of wheels. I'm going to roll them in at an angle like this. Now, if I don't do anything, if I just set the wheels in motion, there's no reason for them to change, right? They're going to keep going along the direction of this arrow, which is their direction of travel, and they're going to roll along here until they get to this boundary. Now, when they get to the boundary, the wheel here on the left is going to encounter the slower speed first. However, when it does that, you'll notice that if I hold it like that, so here's the left-hand wheel down here, but the right-hand wheel is above the boundary. So right when this thing hits the boundary, it's going to slow down because now it's in the grass and the grass is going to make it travel a little slower. But this wheel over on this side is still traveling the same speed that it would on the pavement, right? So that pavement is a quicker speed, and that means it's going to go faster, but they're connected by an axle. So what happens to the direction of travel of the wheels as they move this way and they get caught, the left-hand wheel gets caught in the grass first, it's going to slow down. The right-hand wheel is going to continue to move at its normal pace, and then it's going to hit the grass, and all of a sudden we're going to find that the direction of the travel of the wheels has changed due to that speed being slower in the grass. All right? So what's happening here is as the wheels move through here, they go to this, right? This one is still traveling slightly quicker, and then eventually they get here on the grass, and right, they're going this way now, and now they're going this way, right? So just they're turning, and then they both are in the grass, and now their direction doesn't change anymore. So notice that the what we might say the incident angle, which would be the angle of this arrow right here. So let's just say, if I said the incident angle, which would be that angle there, call that theta I. And remember, why am I measuring to this? Because we measure angles to the normal. Remember we did that? I told you in the mirror case and the reflection case that we were going to do the measuring of angles to the normal of the surface. Why? Because we are going to do it later. Well, here's later. And you know, for reflection, it doesn't really matter. It's just a good habit to be in because we always do it in the normal when it comes to refraction. It's always to the normal. Right? So I'm going to take that normal. I'm going to find that angle, the angle here that the wheels are incident. And then here, I'm going to do the same thing. My normal should be relatively vertical. So this here is our refracted angle, theta r. Now that's going to be indistinguishable from theta r that we use for reflection, but in this case, context. Alrighty? You'll notice that as the wheels are coming on their incident path, like so, okay, they're coming in at this angle like that, and I'm measuring it like this angle here. When they get into the slower speed material, right, they've gone from an angle like this to an angle like this, they've gotten closer to the normal. The normal is now here, and I'm talking about this angle here, right? That's this angle here. So when they go from a faster to a slower, the direction of travel bends towards the normal. It kind of closes that angle up a little bit. Likewise, had I rolled the wheels in the opposite direction, starting down here, right? And I get the wheels here, and I'm going to push them in the grass, going directly along. They're like as if I reversed this arrow, and now it's traveling upwards. What would happen? Well, up here, as it goes this way, the right-hand wheel would encounter the quicker speed first. It's a little bit sketchy, but I think we're okay. It would kind of speed up a little bit. It would go, whoa, 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 right? And it would speed up a little bit. It would turn because this wheel over here is still caught in the grass, and it would go backwards the same way. So the path is reversible. Right? If it comes in and then goes that way, well, if I started here, it would come out and go this way. Okay? We find the exact same behavior with light. Exact same behavior. Right? If I take a faster speed and slower speed materials, I was mentioning air to glass. You'd like to think that glass has a slower speed. It seems like it should. I don't know. How do you like to think of it? It's more dense. It's a solid material, not gas like air. where there's a lot of spacing between the air molecules. There's very little spacing between the glass molecules. Okay, so if I think about light, oops, this pen's probably not going to work. If I think about light, then I can just draw the exact same picture. Right? I'm going to go like this. I'm going to say this is air and this is glass. And the air is slightly quicker. The glass is slower. Where's my boundary over here? I'm getting pretty close to it, about there. You still okay? That's about as far as we should go. All right, so so I just draw the same exact sketch here. So I shine light in like this at an angle, and I find that the normal gives me the ability to measure the theta incident. There's theta I measured to the normal. Oh, we're just missing the glare there. It's going to come down. Here's the normal. It's going to come down like this. And then we're going to find that the light bends towards the normal. And if you've ever looked at a glass of water with a straw in it, this is exactly the shape you'll see. Right? The straw kind of goes like this, and then it goes into the water, and you'll see it's bent. I mean, I think it's the shape you'll see. I should probably test that before I say it. But you'll see it's bent. You probably, right? You've looked into a glass of water and seen that it's bent. All right, so we notice this. Now, I just want to show you what this looks like with I just want to show you what this looks like. Now, I know we can't usually see the red laser, so I went higher and I got one of these things, and these things are pretty serious. These things are pretty serious. You don't mess around with these. I don't even know how Amazon sells these things, but I'm going to guess that Zoom is not going to be able to deal with this because my camera will probably, it's going to notice the high intensity and it's going to really dim the saturation. So here we go. Here's a green laser. Okay, it's on, and I'm going to shine it on the board. Whoa, let's watch the picture go down in the intensity here. Okay, oh, not too bad. All right, so here I've got my block of plastic here, like this. Let's go like this. Okay, so if let's see if we can do it. You can see the laser beam going through there. Oh yeah, it looks pretty fun, huh? Now, if I go at an angle, let's actually mimic the exact same. Let's mimic the exact same picture. Okay, if I go in here, I'm going to come in here. All right, so here I'm going to go like this. I'm going to, right, whoa, come on. I'm going to have my beam, I'm shining it directly on the whiteboard and then just moving it so you can see it goes like that. Can you see it changes direction ever so slightly? And then on the outside as it goes through, right? Well, I think that's pretty good. And look, you got two reflected beams coming up on the top right there. That's awesome. I'm going to move this over a little bit. Okay, so here's the incoming beam there. Boom. Goes down just right. It's not the same path that it used to be. That's the same path. Well, same direction. I don't know if you can quite, yeah, I think you can see that pretty good actually. All right, so it's that bending of the light that we're interested in, right? If I go a little bit more that way, you can get a really good sense, right? Then it's really going at an angle that's steeper in the material than the angle that I'm shining it at on the board, right? Like that. All right. Okay, I'm glad that kind of worked. You got to do something to keep this. Otherwise, it's just video and some guy talking about stuff, and who cares? Okay. we need to have a quantity that that relates actually, take that back. The quantity that we're talking about is the speed of light. So let's talk about speed of light real quick. Speed of light is known as little c, and that is not a very good marker. Okay, we'll go try this one. Speed of light is little c, and just to give you an idea, the number value is not exactly this, but it passes 300 million meters per second, which means that if I took this laser pointer and somehow I was able to curve the light around Earth, maybe I set up mirrors around Earth the entire way, and I shine it, boop, and it goes all the way around Earth, and then I go like this, I go on, off, and then I turn around. It's already passed through me about 7 times. 7 times around Earth. It's about 40,000. Yeah, somewhere around there. So it's fast. Okay, it's fast. When we're interested in a material in which the speed of light is slower, we don't call it c, we just call it v, just like we would for a regular speed. Speed of light in a material. So this is what speed of light, I should have said this a little bit more precisely. This is in a vacuum. Vacuum. And so speed of light in a material depends on the material. We just call that v. So what happens here is that there's a law discovered of how to mathematically represent the refraction of light from one material to another. And it was first discovered in like 980, by a Persian mathematician slash scientist back then. And later on in 1620, it was rediscovered by a Dutch fellow, and it bears his name, Snell. So we call this Snell's law. And it tells us about the relationship of the angles, theta I and theta R. Okay? So what it's telling us is that if we take the sine of theta I divided by the sine of theta R, what we're going to get is a ratio of we're going to get a ratio of speeds, basically, all right? What we're going to find is that it's going to be the speed of light in the incident material divided by the speed of light in the refracted material. So this is V incident divided by V refracted. Okay, for our purposes in air, okay, I'm just going to leave this note here. The speed of light in air is approximately c. So for our purposes, we're just going to examine refraction based on speed of light in air being speed of light in the vacuum. Okay. So for this case over here, V incident is the air, so it looks like this is just going to be C divided by VR. This is the speed in glass, right? We've got refracted speed, and we've got incident speed. Okay, so I've applied this to get to here by saying that the incident speed is c because we're considering air. So VR is really the speed of light in glass. We can calculate the speed of light in glass, but it's such a horrendously large number. 300 million is the kind of starting speed, and certainly it goes down from there, but it may not be a nice easy round number like 3 times 10 to the 8, you might have to then start with decimals and stuff like that. And that becomes kind of cumbersome to carry a factor of 10 to the 8th around with everything. It's just not, appetizing to do that in calculations. So we're going to come up with a slightly different way of considering how to represent the speed of light in a material. It's known as the index of refraction, and it was first coined by Thomas Young in about 1800. And what it does is it basically, in some way, it's the opposite of what we want. It's like you think of how much slower is light moving in glass. Maybe suppose light in glass moves at 2/3 the speed that it normally does, right? Well, instead of making the index of refraction something easy like 2/3, we have to talk about it as being the flip over of that, 3/2. Okay? So this quantity right here is the index of refraction of the refracted material, this C over VR. This is speed of light in vacuum divided by speed of light in the material. This is known as the index of refraction. And in this case, it's the index of glass if the speed of light in the refracted material is glass, right? So this is the index of refraction. It's known as lowercase n, which that didn't show up too well. Let's try that again. Let's go with this one. The speed of light in the material is lower than the speed of light in the vacuum. So this is a fraction that is greater than 1. 1 divided by this, right? V divided by C, that would tell you what's the percentage of light speed that is attainable in the glass, right? So what we would say here is if N is equal to C divided by V, that's if light's traveling at, say, 2/3 C in the glass, then the index of refraction is 3/2. C divided by 2/3 C, and then you flip it over. Okay, so this is a unitless quantity. The index is a unitless quantity. It just represents 1 over how much slower is the light going. Okay, so in order to do this, we can take all of this and kind of bunch it together, and we'll come up with the modern day way of thinking about Snell's law, which is that on the incident, from the incident side, I'm going to have the index of refraction on the incident side multiplying the sine of the incident angle. All right, so this is the incident this is the incident index of refraction times the sine of the incident angle. And we're going to say that on the refracted side, it's the exact same amount, right? It's the exact same quantities. I get the index of refraction on the refracted side and the sine of the angle on the refracted side. Okay, so for those of you who don't like fractions and ratios like this, if you just multiply everything out so you get rid of the fractions, you come up with this. And that is known as Snell's law, at least in the United States it is. If you go to France, it's known as the Descartes-Snell's law. If you go other places, it's other... People discovered this in different points in time, and for some reason, this guy got his name attached to it, and I don't know the reason for that. Probably because he paid a lot of money to somebody to say, hey, put my name on this. I know it's been around for 700 years already, but never mind that. All right. So when I say that V of air is approximately equal to C, what does that mean about the index of refraction of air? N of air is approximately 1. C divided by C. Therefore, when you look at something like this, right, you can kind of go back to recreate this ratio reasoning. If I swing the sign underneath this sign and I recognize that this n is equal to 1, then it becomes the ratio of signs equal to the index of the refracted material, and that's what we had going on right here. All right. Okay, let's take a look at a couple of quick examples here with this. I want to what do I want to do? I want to go through maybe show a couple of, kind of like we did with lenses last time. Not lenses, mirrors last time when I talked about the focal point equation, the mirror equation that we used. Let's maybe examine a couple of case studies real quick and see if we can't figure some interesting stuff out. Let's go here. Let's do this. So I want to go back to that plastic block that I just had. Okay, so I've got this block. I was shining a light in this way. It was refracting inside here and then coming out. So let's talk about that process a little bit. All right. So by way of a case example here, let's examine. Yeah, can we do this? Let's examine a chunk of material here which has an index. I should preface this by saying when I say a material has an index, I'm talking about the index of refraction, and I mean that it's not 1, it's greater than 1. Right? So the speed of light's slower than c in these materials. Let's assume that this has an index. We'll just call this n. Out here is air. Okay, so this is air. Here, air. Here, and then this is, say, the block of plastic. Right, so I've got this thing right in here. Let's now go with light entering the material from the upper left like this. Let's give it a little bit more, slight more angle than that. A little more angle than that. There we go. Okay. The incident angle here in air, I'm going to measure that to the normal. I'm going to just say, yep, drop in a normal here. And I'm going to say, yes, this is my theta I right there. I'm going to examine the path that this thing takes. I know that it's going to bend a little bit more steeply. It's going to be more angled towards the normal, so maybe it comes in like this. Like that, such that, as I've showed before, that is our refracted angle, theta r. And then it's going to come out from the material and go back out into air. It's going to do the exact opposite of this process. It's going to start in the material here at this angle and then go out and come away in air. It's going to come out like this, like so. Okay, and I think that's what we observed when I shined the laser through the block. At least, hopefully, that's what you were able to see. I thought that's what I was able to see while looking on the screen. So hopefully Zoom didn't mess it up completely. But nonetheless, let's go with this. So we've analyzed the situation in which light goes from the quicker into the slower material. And that's what's happening at the top boundary. Question, what angle is light emerging from the block when it goes back out into air? At what angle is it coming back? How do we show something like this? Well, first of all, we can write Snell's law for the first change in direction here up at the boundary. So here, and put a dot right there. You can apply Snell's law at that dot. And it's going to look just exactly like this. Incident times incident index times sine of theta incident equal to index in the refracted, sine of theta angle refracted. All right? Now, when I go to this dot down here, which is the emerging boundary, the question is, okay, where's the incident angle? Where's the refracted angle? Well, now I have to switch these around. Now look, at this dot, for this lower case, this is the incident angle, and this is the refracted angle. Okay, so whenever you're dealing with applying Snell's law to a boundary, to a transition, first things first. We always apply it right where the light hits the boundary, okay? We look at the path of the light up here, we look at the path of the light down here, but we're really applying it right there so that we're dealing with the angle that it came into that point at, and it's the angle that it's refracted away from that point, okay? So those are the two angles. Whenever we have a boundary transition, we're looking at the incident angle and the refracted angle right in that neighborhood. I'm not applying it from here down to there and doing like, no. It's always right in the neighborhood, okay? Second thing, when I'm in a material and the light beam is emerging, that means the material is now the incident material. So when I look at Snell's law here for incident material, that's now all, instead of being air, that's now inside the plastic. And the refracted is now being in air, because it's the exact opposite of the incoming case. Here we were going from air into the plastic, so we were going, air was the incident material, plastic is the refracting material. Now when it's leaving, I have to do the opposite. I have to go, incident material is the plastic, refracted material is the air. Okay, so just be aware of that. I find that it's often a common thing that people get caught up in, air is always the incident material. It's not. Whatever the incident material is the incident material. It's just convenient that we start talking about it from the air perspective, but light does shine from inside things out into air, so then you have to switch around. If I write Snell's law up here, let's call this point number 1, and this is point number 2. All right, so at point 1, I'm going to apply Snell's law, and I'm going to say that the incident, actually, you know what? I'm just going to I'm going to subscript everything with the material that it's in. So I'm going to put air, sine of theta in air is going to equal, I don't want to write plastic. I'm going to put P for plastic. Sine of theta for P. Okay. So coming in here, this is my theta in air, and this is my theta in plastic. Okay. So the reason I'm doing this is because theta I and theta R are general terms. It's the incident angle and the refracted angle. All right? But the material that the incident angle is measured in changes. So it's nice to sometimes give it a more specific name so that you know, hey, I'm talking about this angle, like theta 1, or theta A, or theta B, or theta 1 to theta 2, or something like this, okay? So notice that when I apply it here at point 1, I'm going from air, like this, into plastic like that, okay? Now, when I apply it at point 2, okay, now I'm reversing the situation. Not only that, but look, are the angles the same? Is this refracted angle the same as this incident angle? The refracted angle at point 1 and the incident angle at point 2, are they the same angle? Will they always be the same angle? Maybe also think about that as a question, okay? In this case, these two angles are the same because these two boundaries are parallel, and this is a normal that has the same direction through both boundaries. Therefore, the angle that this ray comes into the material at is the same ray that it's incident on this point and leaving, okay? So the refracted angle it comes in from point 1 equals the incident angle here at point 2. Now, is that always the case? Of course not. I could certainly consider this lower thing to be angled. If I have an angled surface, now the normal has a different direction and I have to measure a different angle. So this is where you let your math and geometry skills just look at the situation and take over. Don't memorize like particular cases of these, right? Know what the law is. Where is it? Here. Know what the law is and let the geometry of the situation dictate how you apply it. Okay? So that way you always are applying the law and then you have in mind what your picture looks like. All right, so here at point 2, I'm going to say, well, the incident angle is the same as the refracted angle, so I'm going to call that NP. So NP times sine, sorry, I said angle, so I'm going to call that theta P. Theta P. That should equal N air times sine of theta air. Okay, is this shocking? Well, probably not, because it is the exact reverse of the situation at point 1, right? At point 2 is the exact opposite of the situation at point 1, the exact reversal of it. So what this is telling us is that the outgoing angle should equal the incoming angle, right? The overall outgoing angle of the light into the air should equal the overall angle at which the light started in the air and then entered the plastic, right? It's gonna, that angle up there should equal this angle down here. And the angles being the same doesn't mean they're exactly on the same path, but they would be parallel and displaced by a little bit, okay? So this is one way to look at that. And this would be true for multiple parallel surfaces. Okay, if I just sandwiched a whole bunch of surfaces on one and said, what's the outgoing angle? All you got to do is chase Snell's law from 1 to 2 to 3 to 4 to 5 and out it goes, and you don't have to do any real calculating because you can see if you just apply Snell's law 1, 2, 3, 4, 5, it's going to go out at the same angle that it comes in because all of these things are the same due to the surfaces being parallel. Now, as soon as the parallel surfaces disappear, then this is all off the table, okay? So for example, suppose that we have a situation like this, where I've got a material whose boundary looks like that. I've got a material on this side, on this side of the boundary, and I got a material on this side of the boundary, right? So I might say, well, look, let's shine light in. It comes in like this, hits right there, right? So this is, say, N, I'll just call this N1, and I'll call this N2, okay? So here it goes in and goes in at some angle there. It's going to refract. How is it going to refract? I don't know. Depends on what the indices are. Let's just suppose it comes in here, that's where it was going. Let's suppose it's refracting, oops, let's do this. Let's suppose it's refracting this way, like that. Okay, now it comes into this situation here. I've got a normal that I'm dropping here, and it's going from there, what's it doing? It's going a little further, right? So it went from lower angle, higher angle. So this has to be lower angle. So it's got to go like this. Higher to lower. Is that right? I think that's right. So it comes in here, that's the incident angle like that, theta I, or call it theta 1. Here's this is theta 2. Like that. And then that would be the case for this point right here. I could apply Snell's law at that point. Then I'm going to look down at this point here, and I'm going to say, oh, I've got a different angle than theta 2 here, because the normals change direction. Right? So now I have to think about, okay, I've got to figure out how to get this angle here, and then eventually figure out what this refracted angle is here. All right? Okay, so let me do this. Okay. Let's go ahead and take a look at putting some numbers onto this situation here. All right? The way I have it drawn, and this is something that maybe you'll eventually come to be able to recognize quickly, is that if I look at just the first point up here where I'm going to apply Snell's law up there at that point, the incident angle in N1 is some amount, whatever it is. But notice that theta 2 is larger than theta 2 is larger than theta 1. So the refracted angle is greater. What does that mean? Well, let's take a look back at this thing here. If the refracted angle is greater than the incident angle, then it's not like this case. But it is like this case. So what that tells you is that light is speeding up, going from N1 into N2. What does that mean? It means the index of refraction of N2 we would expect to be less. Right? Because it's got the opposite relationship. The index of refraction N2 we would expect to be less than N1. Therefore, if I'm going from a lower index to a higher index at this one, note that I would expect the angle to change more like it does on the top up here where it bends towards the normal. So that's why I was trying to be a little careful with, oh, how do I draw this here? I came in at kind of a steep angle here, but now this angle is really steep. Okay, because the light ray is going to refract towards the normal as it goes from a material with a lower index and the speed of light is faster into a material with a higher index and the speed of light is slower. Okay, this then mimics glass into air and then air into glass, for example. All right. So let's go ahead and throw some numbers onto this and see what happens. We'll just do a sample calculation of this here. Let's suppose that N1, this has to be a higher index. So let's suppose this is something like 1.8. And let's suppose that N2 is 1.2. So that way I can avoid having air in here. Okay. Let's say that the light is coming into the first boundary, theta 1. Let's choose something nice and easy like the sine of 30 degrees. So let's just choose theta 1 to be 30 degrees. And then the next thing is find every other angle. Okay. Let's suppose that theta 1 is 30 degrees. Okay, so example. Find the other angles. So I'm going to apply Snell's law at the first big dot up at the top here where I know the incident angle. Incident angle is theta 1. I know the two indices, so I should be able to figure out theta 2. Okay, let's start with doing that. I'm going to call this point A, and I'm going to call this point B. So at point A, I'm going to apply Snell's law, and I'm going to start with all the incident stuff, incident index, incident angle. Let's do this. Okay, point A, I'm going to have N1 times the sine of theta 1. And that should equal N2 times the sine of theta 2. I'm looking to figure out what is theta 2. So I'm going to solve. I really don't like solving with arc sines. So I'm just going to write an expression for the sine of it and then find what the angle is from there. I'm just going to swing N2 underneath all of this stuff here. And I'm going to say that sine of theta 2 is equal to N1 divided by N2 fraction multiplying sine of theta 1. From that, we can determine theta 2. Since we have these numbers, I can plug these numbers in, and I can tell you that if I take N1 to be 1.8, divide by 1.2, and multiply by the sine of 30 degrees, that's like 18 over 12, which is 3/2. And 3/2 times sine of 30, that makes it 3/4. So I'm looking for the angle whose sine is 0.75. I don't know that off the top of my head. Since I just made up this example, I'm going to have to calculate that one. I don't have, it's one of my, I don't know if a failing is quite the word, but I suppose that's a failing. Let's do in 0.75. So that angle is 48.6 degrees. That's what I got. Theta 2 is 48.6 degrees. Am I concerned about significant digits? Not really. I know I have 2 everywhere and I just carried 3 into that, so if you want to call it 49 because that's what you want to do, fine. I just wouldn't put in a string of, well, it was 48.590377984. No, just round it nicely. Okay. So say it's about 49 degrees. That is just theta 2 though. I want to go back and find all the other angles, so I still have 2 more angles to go. How do we do that? Well, I'm going to now apply Snell's law at position B. Now my incident index is N2, right? My incident index at point B is N2. Now I have to find the sine of theta. What do we want to call this? It can't be called theta 2 because that's not theta 2. It's got a different angle. So I guess I'm going to call it theta 3. And I'm going to go to N1 times the sine of theta 4. All right, so here, I'm losing this pen a little bit. Theta 4 is that angle down there. Theta 3 is this angle right here. Let's see. That seem look okay? Getting a little busy, but I think you can still make it out. But I have one equation with 2 unknowns, so I'm stuck because I don't know theta 3, I don't know theta 4. Good news, however, I can geometrically figure out theta 3 by looking at the triangle formed with theta 2. I'll draw this in a separate thing over here. So my light ray coming this way from point A to point B has a normal which comes this way. Oops, missed point B a little bit there. It has a normal which comes this way, and that makes a 90-degree angle with the normal from the side down here. Right? Those 2 normals are at 90 degrees. So this is theta 2, and this is theta 3, right here. So this is just a complementary angle. Whatever this was, so theta 2 is 49 degrees, and what does that mean? 41 degrees, right? 49 and 41 make 90. Theta 1 should be 40, theta 3 should be 41 degrees. And now that I have theta 3 from that setup, I can go back into here and pop it in, deal with my indices, and solve for theta 4. So let's go do that. Sine of theta 4. I always encourage this step of algebra. It seems pedantic, but I encourage this step of algebra because it helps take away any, oh, you just go, oh, I just got to divide this by this and do it, right? If you suddenly do it, and it's easy to kind of make an algebra mistake right there. So I'm going to do, what am I doing here? I'm doing n2 divided by n1 times the sine of theta 3. And theta 3 we know, and n2 we know, and n1 we know. So take a look at this fraction. It's going to come out, this is going to be the sine of theta 3, and then this is a fraction which is less than 1, which is going to knock this number down even more. What that tells us that the sine of theta 4 is going to be a low number, therefore theta 4 is a smaller number, right? So we can find theta 4. Oh, I put this equal to, hold on a sec, let's go ahead and put numbers in here. So I put equal to 1.2 divided by 1.8. Those are the indices, and then sine of 41. Sine of 41 degrees, and that gives us theta 4. And I don't know that number exactly off the top of my head either, because I don't know the sine of 41 degrees. So this is a situation where we are going to go sine of 41 degrees multiplied by basically 2/3. And now I am going to hit that with the inverse sine of that thing right there. And so this comes out at about 26 degrees. Alrighty, and so my picture turns out to be qualitatively correct in the sense that I'm thinking about the index of each material, and then how does the light bend based on the index, right? So whenever the index gets larger, the angle shrinks. Why? Because this is a direct proportionality here, right? It's, well, that's a direct proportion, but this by itself is an inverse proportionality. In other words, if that goes up, then this goes down, okay? In order to make it be equal to the same number. Therefore, when the index increases, the theta decreases, and when the index decreases, the theta increases. And we only ever deal with angles between 0 and 90 degrees, because you can't have an incident angle which is going to be 90 degrees, because by then it's not incident on the material, right? An angle of 90 degrees goes like this and is missing the material. So your your light is not refracting at this point, okay? Okay, so that's a situation of Snell's law as applied to a situation where light refracts easily from one material to another. Let's ask the question here when I examine one particular case. What happens when I talked about the incident ray being 90 degrees. What happens when the refracted ray approaches 90 degrees? Huh, that's interesting. So, if the refracted ray is approaching 90 degrees, what do we do with that? Well, this is a fun topic because it gives rise to a very interesting phenomenon. And it is one that we use, caution, do not shine laser into remaining eye. It is one that we use in order to send information from one point to another via, nowadays, lots of things are turning wireless, but the reason they're called wireless is because we used to have wires. There used to be large cables connecting things, and in fact, there still kind of are. And people who have those companies that provide home internet might be on a wired system, okay? Well, that wired system probably involves a fiber optic cable. Fiber optic cables work by this process. So let's see if I can get this to happen here. Let's see if I can get this to happen reasonably well. Whoops. Okay. I don't want that, I want this right here. I want to get this up here like that. Okay. Now, if I can hold this, I want you to look at the beam. I want you to look at the beam. All right, you see that it's bouncing off that lower surface. This is not a mirror, this is just plastic. This is just a plastic block. But notice it's bouncing right off that lower surface. And I can make it not bounce off the lower surface if I go up a little bit more. Maybe I can find where it would emerge from in here. Almost. No, now I'm hitting the glass. Anyways, point being here that I can find an angle where the light is coming incident onto a boundary and not leaving the material. Right? So this is pretty interesting because this is a transparent material, and air is a transparent material. Light is incident onto the transparent material boundary and reflects off. This is a really cool phenomenon. It goes by the name of total internal reflection. Reason being, you saw all the light going in and bouncing off, so it's total. The light all stayed within the block, it's internal, and it reflected, so total internal reflection. Now, there are restrictions on this. This can only happen when the material is going from a slower speed to a higher speed. In other words, a higher index to a lower index. Whenever it's going from air into something, this will not happen because nothing, more or less, nothing we're going to talk about has an index lower than air. That's 1. You don't have a lower index than air. Okay, so this happens going from a material with a higher index to a material with a lower index. All right, so note, this is only higher N to lower N. Will never happen going from air into glass. That you can't have this happen. You can't reflect light in air. But I can reflect it into the and keep it into the glass or the plastic. I can do that. So let's take a look at a couple of diagrams to see what this looks like. Okay. Here's that lower boundary. I'm gonna no, we can do it. So, let me get away from the glare though. Let's see, where's better? Just down here. Okay, so this is air down here, say. And this is plastic or glass or whatever you like up here. All right, so I'm going to do glass into air, and I'm going to draw a succession of rays. Okay, so I'm going to suppose that they're incident on this point here. Now, supposing that they're coming into the glass, they're coming into that point at some angle in the glass. They're going like, say, this. Okay, bigger point. And then they refract, and they go out like that. Okay, so this is a typical situation for higher index to lower index, right? The angle widens. Okay, this angle here, you'd say, well, my normal, right, looks like that, and that angle right there is my refracting angle. This here is my incident angle. like so.
Now, I spent a lot of time skipping rocks on lakes, right? So how do you skip a rock on a lake? Well, you take the rock and you don't that's not going to skip it, okay? So imagine that you're throwing the rock and it's going into the water. Now, okay, maybe it's not refracting like that. It's not exactly a perfect analogy, okay, but you don't want the rock to go into the water.
You want the rock to skip off the water. You want reflection. So how do you get that to happen here? Well, you shallow the angle out a little more, right? So instead of that angle, maybe I go at this angle, right? Instead of throwing the rock like this, I start to throw it more like this. Okay, well what that caused, it didn't quite do it there, didn't quite skip. It still went in. So that means it came off going like this. Got an even bigger refracted angle. Still is leaving. Okay, so now I'm going to sidearm the thing, right? And we're really going to get down and have the rock skip. Okay, so now I'm going to have it go all the way. I'm going to have it like this. Whoa, all the way down here. It's coming in at this angle like this. Now, right, if I get just the right angle, because you'll notice that there's an angle at which, right, can you see the refracted ray is slowly ticking upwards towards being in the material and not leaving. So there is an angle at which you have just barely started to achieve this reflection. Okay? So it goes in, it goes out. All right? Now, we can treat this is a reflection now, okay? This is a reflection, which means, here's the normal, I'm going to make it really big, which means that the reflected angle, which is this angle here, that reflected angle should equal the incident angle, which it does. This angle here, those two angles are the same because it is a reflection. But we can treat this reflection with Snell's law and refraction by using the model that the refracted ray refracts at an angle of 90 degrees. In other words, what that means is that the refracted ray, okay, here's your incident ray coming in like this. That means that the refracted ray is going like this, straight that way. Okay, is that true? No, that's a bit of a fiction because we've transitioned from a straight refraction into a reflection. But we're using the refraction model to analyze a reflection. Okay, so this is a bit of fiction, but it works. And what we do is we say that the refracted angle is 90 degrees. Okay? When we say the refracted angle is 90 degrees, then what we are implying is that the incident angle is the angle that this reflection first starts. Okay? Now, notice, if I get the skipping, if I find the angle where skipping works and I go even more shallow than that, I definitely have more skipping. Okay? So my incident angle can be, you know, the one where I just get it to start, or it could be even more than that, right? But when the refracted angle is 90 degrees in our Snell's law, that tells you that the incident angle is the angle at which this barely first started. You're picking that very first angle of incidence at which you have a reflected beam here. All right? That angle is known as the critical angle. It's the angle at which you transition from refraction and the light leaving to reflection and the light not leaving. That's the critical angle. All right? When that refracted angle is 90 degrees, the incident angle is the critical angle. Okay? That's the critical angle. Theta C is the universal symbol for this, theta C. All right, so that means if I said that this angle was the first one at which it happened, then this angle is theta C, and therefore that angle is reflected and is also theta C. All right, so you're saying, well, wait a sec, what's this refracted angle being 90 degrees? Where's that all coming from? Remember, that's a convenient fiction to try and describe, using the model that we have, what's happening here. And it turns out it works really well, okay? There is no actual refracted ray. So we set the refracted ray to maximum angle and say, after that, we don't have refraction, right? That's kind of the last time when refraction, see, remember how I was telling you that you couldn't have a 90-degree incident angle? You could have an 89-degree angle, sure, but 90-degree, you don't have refraction anymore. Well, it's the same thing with this. At 90 degrees refraction, I'm saying that we don't get a refracted out beam anymore. We get a totally internally reflected beam, okay? So check this out. Let's apply that to this situation up here. I'm going from a 1.8 to a 1.2. That satisfies the criterion, higher end to lower end. Let's try and find out what's the critical angle. In other words, what angle would I shine this beam at in order to achieve a reflection completely in material 1 right here? And not have any light enter material 2. At what angle would I shine that? Okay. So, at what angle does the light not leave material 1? Or should I say, does light not enter material 2? Okay, and this is disguised as, okay, find the critical angle, because now you're talking about internal reflection. And I apologize, I think my markers are slightly running down on ink right now, but I don't want to stop and then take your time up to refill them, so I'll press harder and write bigger. And then we'll just make it, because we're almost at the end here. So at what angle does light not enter material 2? That is, find this angle up here. Now, what we have is this whole thing has changed, right? This theta is question mark, and none of this is happening. It's doing this. It's going like that now, okay? So we're going to erase all of this, and we're going to erase all of that. And we're going to say, okay, what angle do we shine that in so that we don't get anything into that material too? Well, that means I'm going to find the critical angle. This is thinly disguised as find theta C. Okay, let's set up Snell's law for a theta C example. All right, I'm going to start with N1. Material 1 is where light begins. So N1 times sine of theta 1, but theta 1 should equal theta critical. So I'm going to change that to theta C. This should equal N2 times the sine of the refracted angle. But remember, when we're talking about a theta C incident, the refracted angle is 90 degrees. So this is the sine of 90 degrees, which you cleverly recognize is equal to 1. Therefore, finding the critical angle is simply that we take sine of theta C and we set it equal to N2 over N1. Now you see mathematically why it must be higher n to lower n, because if it was the other way around, I would get a fraction here which is greater than 1, and I'd be trying to take an arc sine of that. That's not going to work, you know that. So this fraction had better be less than 1, okay? In this case, it's going to be 1.2 divided by 1.8, which at last count was the 2/3. So what's the sine of 2/3? Let's do this. I don't know these signs off the top of my head. 0.67. This is about 42 degrees. Oh, of course it's 42. theta C is 42 degrees. Right, so if I shine light coming in at that angle at 42 degrees or more, I would get complete reflection in material 1, and no light would enter material 2, and that would be internal reflection. And this is how light is shined at into a cable and then bounced great distances. The signal loss is minimal because they have engineered the appropriate index such that outside, right, the fiber optic itself has a particular index, and then outside that index, they've put other materials with other different index such that the light never goes outside of that material. And therefore, in this case, if I were to say I'm going to have a boundary on both sides, I would call material 1 a fiber optic cable, because I could confine the light and it would just bounce back and forth within there. All right, I think that's going to do it for today. That's Snell's law and refraction of light through different materials. What we're now going to do is take this thinking and start designing optical instruments such that when the light shines through them, it refracts and produces an image on the other side of the, in this case, what you probably recognize as a lens. Okay, how does glass and the shape of the lens affect what kind of image I'm going to get when light is shining in? So we're going to pick up tomorrow talking about lenses and the images we get when we shine light onto a lens. So we'll pick up there tomorrow. Remember to please keep working on the homework. It is due in 1 week. And so that means you probably should be done with the reflection stuff. We had a couple of questions on that and a couple of problems on reflections. We're going to start on the refraction stuff. So after today, you can start attacking some of the refraction problems. So please stay up to date on that. It's homework set 1. You really don't want to get behind, especially in a class like this. Alrighty. So that's my that's my spiel to you. Have a great rest of your day, folks. And I hope that things are going well. If you have any questions, reach out, fire me an email, let me know, and I will see you in the next video, which I was going to say see you tomorrow, but maybe you all watch these at different times. Happy day, folks. Ciao.